All right, let's just dive straight into this explainer and tackle what is arguably the most feared mathematical concept for 11th and 12th grade physics students. We are going to break down integration, strip away all the unnecessary complications, and basically build you the essential physics toolbox.
You know, I want to start right here by validating what so many commerce and science students already feel. Integration is the most frightening chapter in 12th math. It's a sentiment echoed in classrooms literally everywhere. But today we're going to flip that fear entirely on its head. So here's our roadmap for today's analysis. We've got 1. Integration without the fear. 2. Adding infinite tiny pieces. 3. The basic power rules. 4. Constants in multiple terms. 5. Basic trigonometric integration. And finally, 6. Definite limits and boundaries. And honestly, here's the best part. This simple 6-point list is literally the only integration toolkit you're going to need for your entire high school physics journey. All right, let's hit section 1. Integration without the fear. Let's start by separating the heavy math from the practical physics.
See, while a math student might spend months agonizing over a dozen textbook exercises full of these incredibly complex derivations, as physics students, your burden is actually incredibly light. You really only need a handful of basic formulas meant purely for practical application. You have absolutely zero need for complex product rules and zero need for complex dividend rules. In fact, you can learn everything you actually need for your physics courses in under 30 minutes. How great is that?
Moving on to section 2. Adding infinite tiny pieces. Now, before we look at any equations, let's establish exactly what integration actually is out there in the real world.
This brilliantly illustrates the core difference between two concepts that honestly get confused all the time. Summation is for adding finite pieces. It's totally countable. Think of taking 5 2-meter chunks of a rod and adding them together to get a total of 10 meters. Easy, right? Integration, on the other hand, is the mathematical tool we use when the pieces are infinite. It's exactly how we add together an infinite number of microscopically small pieces to find a total.
And to do that, we use a specific notation. So when you see a dx or a dA, please don't panic. It literally just represents a single, infinitesimally small piece, a piece of length or area so incredibly small that it's smaller than anything you can possibly imagine. We're talking essentially almost zero. It is the absolute smallest fraction of a larger whole.
So the crucial takeaway for your exams is this foundational rule right here. If you use the integration symbol, you know that stretched out s, to add up an infinite number of those tiny dx pieces, you simply get the whole variable x. Similarly, if you integrate all the infinitesimally small dA area pieces, you just get the total area a.
Okay, section 3, the basic power rules. Let's move to the most common scenario you're going to encounter in physics, which is variables with powers. Remember how in differentiation you pull the power down and subtract 1? Well, scratch that, forget it for a moment. For integration, instead of memorizing some confusing formula, just remember this really simple 2-step mental checklist for the power rule. Step 1, add 1 to your current power. Step 2, put that exact new power in the denominator.
For instance, let's look at the integral of x squared. You add 1 to the power of 2, making it 3. Then you divide by that new power of 3. So x squared becomes x cubed over 3. Simple, right? Now, quick heads up, there is a strict boundary to this rule. This formula absolutely does not work if the power is -1, simply because dividing by 0 is mathematically undefined. There actually is a special logarithm rule for that specific case, but you won't even need that for months in your physics curriculum, so we're just going to keep our focus really tight today.
Right, section 4, constants and multiple terms. Next up, let's look at what happens when numbers in multiple terms crash the party.
Notice how a constant attached to a variable behaves completely differently than a lone constant. If you have a constant attached to a variable, like the 3 and 3x squared, it just steps aside safely. You literally just pull it outside the integral and solve the x squared normally. But a lone constant is a whole different story. If you just have a lone 3 dx, it absorbs the dx and becomes 3x. This is a vital light bulb moment for you. Unlike differentiation, where a lone constant just turns to 0, in integration, it actually gains the variable.
And hey, if you have a long string of terms added or subtracted together, you simply chop them up and integrate them individually. You take the x squared and integrate it on its own, then you take the 4x and integrate it on its own. You can do this whether you have 2 terms or 20 terms. It's basically plug and play.
Okay, section 5, basic trigonometric integration. Let's quickly drop 2 crucial trigonometric formulas into our toolbox.
Notice how the minus signs flip compared to what you originally learned in differentiation. Honestly, it's a trap so many students fall into. In differentiation, the derivative of sine is a positive cosine, but in integration, the integral of sine is a negative cosine. Conversely, the integral of cosine is a positive sine. You definitely want to burn this switch into your memory.
Finally, Section 6, Definite Limits and Boundaries. Let's finally bridge the gap between abstract math and real-world physics answers. Up until now, we've only really looked at indefinite integrals, which give variable answers, like x cubed over 3. But in physics, we usually aren't looking for an algebraic expression, are we? We want a specific, concrete number. We're adding things up from a specific starting point to a specific ending point. And we get that concrete number by integrating between a lower limit, which is our initial point, and an upper limit, which is our final point.
The workflow for this is wonderfully simple. First, you do the integration normally, using your basic power rules. Second, take your result and plug in the upper limit. Third, plug in the lower limit. Finally, just subtract the lower result from the upper result. Final minus initial. That is literally it.
Let's see that actually in action. For example, if you integrate x squared from a lower limit of 0 to an upper limit of 3, well, the integral of x squared is x cubed over 3. Plug in the upper limit of 3, and you get 27 over 3. Plug in the lower limit of 0, and you just get 0. So the math just boils down to 27 over 3 minus 0, giving us a beautiful, concrete answer of 9.
All right, now that you have the complete physics integration toolbox, how will you apply these exact steps to solve this homework challenge? Can you navigate the negative power? Remember the power rule checklist we talked about and successfully apply the definite limits? Work through the exact steps we just outlined and see if you can nail down the final concrete number. You guys now have the exact toolkit to completely conquer the most feared chapter in math. Good luck.